Alright, hello everyone. I hope all of you are doing great. So today we are going to be discussing the solutions to Codeforces Round 812. This round just finished about an hour and a half ago. Talking about the round, I think at least for me this round was a bit trickier than usual. Not a bad round at all, but I found the problems to be a bit trickier. And I was actually quite surprised by the speed with which the number of successful submissions was increasing. Uh, but yeah, uh, overall a nice round. Problem D was nice, and C was a bit tricky for me. I admit that. I'll be discussing the first four problems. So yeah, without any further ado, let's start with the first problem. So this is a pretty easy problem. So here we are given a Cartesian plane x comma y, and we are given n points, that is the x and y coordinates of all these n points, right? And basically, we are living in this infinite plane, and in one move, we can go in any of the four neighboring directions. That is, we can either go up, go down, go left, or go right. Right. So the condition is that we have to go to all the points, all the given n points, and we have to find the minimum number of moves that we have to perform to go to all of these points if we have to start as well as finish at point 0 comma 0. Right, so that's the problem. So we will start at 0 comma 0 and we will finish at 0 comma 0, and we have to reach all these points and we have to come back. So that's the problem. So let's just have a look at the solution. This is a pretty easy problem. So the only observation that is required to solve this problem is that if we go right by x, then we have to come back by x, right? So this is the only observation that was required. So if we are going right by an amount of x, then obviously we have to come left back to 0 by traveling the same amount x, and that is how we will start from 0 comma 0 and we will end at 0 comma 0. And so the same applies for if we go down, and the same applies for if we go left, and the same applies for if we go down, right? So the solution is simple. So we take the maximum right that we are going. So we take the maximum right that we are going. So we like the maximum distance by which we go right. Let it be x, and then add 2x to the answer. Right, this is the simple thing that we have to do here, and then we have to repeat this for all the four directions, right? So repeat this for all four directions, and this way we can solve the problem pretty easily. So yeah, this basically completes the solution. Let's just have a look at the code. So the code is pretty simple. So what you can do is you can create two vectors for x and y, and you can sort both of these vectors. Then basically you just have to check whether you are going right or not. So if x of n is greater than 0, that means you are going right by x of n, and so we can just increase the answer by 2 into x of n. Similarly, if x of 1 is less than 0, that means we are going left by minus 1 into x of 1. So we just add 2 into minus 1 into x of 1 to our answer, and we do the same thing with y. So yeah, this basically completes the solution. And yeah, I think this was a pretty simple problem, a very good problem for a Div-2A, I suppose. So yeah, that's about problem A. Let's now talk about problem B real quick. So in this one is a bit tricky again. So in this problem we have been given with an array A of n integers. All of them are positive integers, and in an operation we can basically choose two indices L and R and decrease all the elements from L to R by 1, right? So we will denote by FA the minimum number of operations which are needed to change the array A into an array of zeros, right? All of the elements converted to 0. And so our task is to determine if for all permutations B of A, f of A is less than equal to B condition is true or not. That means f of A would be smaller than or equal to f of B for any permutation B of A. If that is true, then we have to output yes, otherwise we have to output no, right? So yeah, this is the problem. I hope the problem is clear enough. Okay, so problem B. Let's have a look at the solution now. Cool. Right, so I will just write down the main observation which is required to solve this problem, and then we'll see why that observation is true. So the main observation is that if we greedily greedily try to reduce all the elements to 0, then all the non-zero elements which are there in the array must form a contiguous segment. So if we greedily try to reduce all the elements to 0, then all the non-zero elements should always form a contiguous segment. Okay, so this is the condition which is required for answer to be yes. Now let's see why is that the case. So first of all, what is the minimum number of operations for any permutation? So the minimum number of operations can be found out by just looking at the sorted version of A. So can be found out by looking at the sorted version of A. So the sorted version of A is also a permutation, right? So the minimum number of operations which are required will be there in the sorted version, and that minimum number will be the maximum element of A. So maximum element of A, and the reason being that obviously we need at least these many operations. Let's say this is mx, so we will need at least mx operations, because in every operation the maximum element can decrease by at most 1, so we will need mx operations. But if the array is sorted, then we can just keep taking the suffix which is non-zero, and then we can just keep decreasing it, right? So we can keep taking the non-zero suffix and keep decreasing it, right? So if we do this, we are sure that in exactly mx operations our array will become exactly 0, and so this is the minimum number of operations which is required. Now our task is to tell whether or not in our given array A we will take mx operations or we will take more than mx operations. So I have already written down the main condition which should be true. So let's see why that is true. So let's say that we are greedily trying to reduce all the elements to 0, and we encounter a situation where there are a few non-zero elements, then there is a 0 element, and then there are another few non-zero elements, right? So let's say we have a situation like this, that there are a few non-zero elements like this, and then there is a 0, and then there are another non-zero elements like this, right? So let's see what happens. So now basically, since this entire array has now been partitioned, so this was our array before, but since this element has become 0 now, what happens is that we can't do any operation where L is from here and R is from here, because that would reduce this 0 to -1, and that is something we can't do. So now we have to apply operations separately on this version and separately on this version, and so the number of operations which will be required would be at least mx1, which is the max element here, plus mx2, which is the max element here, right? Whereas we know that for an array the minimum number of operations is the maximum element of that array, so the minimum number of operations should ideally be maximum of these two, right? So it should be mx, which is the maximum of mx1 and mx2, right? And obviously mx is strictly smaller than mx1 plus mx2, because mx is just one of these two, right? mx1 or mx2. So this proves that if we are greedily trying to reduce all the elements to 0, then all the non-zero elements should always form a contiguous segment. Cool. Now when will this condition be true? So let's see when this condition will be true. So this condition will be true if and only if all the zeros that are being formed form a suffix, so form a prefix and a suffix, right? So that is pretty natural that all the elements which are non-zero remain in the middle, and all the zeros are either in the prefix or in the suffix, right? So yeah, that is something that we want. Now when can we get that? Now it is pretty natural to think when can we get that, and we can get that only if and only if our array looks something like this. So it is increasing first and it is decreasing then, or maybe it is only increasing, or it is only decreasing. So like these two cases are just a sub case of the first case. So what we want is, we want our array to first increase and then decrease, or maybe only increase, or maybe only decrease, right? Now the reason for this, now obviously here I am not I am ignoring elements, I am ignoring that neighboring elements can also be equal. So yeah, that can also be true, that neighboring elements can also be equal. So that will only be counted in as increasing or decreasing, because they're just the same, right? So yeah, so The answer will be yes if and only if we have an array like this or this or this. And in other words, basically there should be no index I such that the maximum element in 1 to I minus 1 is greater than A of I, and the maximum element in I plus 1 to n is greater than A of I. Right, so this is the only condition. It's pretty natural that if this happens, then we will have a local minima, and a local minima means that there is our array is first decreasing and then it is increasing, and that is something that we don't want. So if this is true for any I, then answer is no, and if this is not true for any I, then answer is yes. So yeah, this completes the solution to problem B. Let's just quickly have a look at the code. So the code is pretty simple. We first pre-compute the prefix maximums, and then we pre-compute the suffix maximums, and then we go from 2 to n minus 1, and we just check if the prefix maximum at I minus 1 is greater than ai, and the prefix maximum at I and the suffix maximum at I plus 1 is greater than ai. If that's the case, then the answer would be no, and if that's not the case, then the answer will be yes. Right. So yeah, this completes the solution to problem B. Let's now move to the third problem, problem C. Okay, so talking about C, I think for me this problem was a bit problematic and I got stuck on it for quite some time. And my solution is also a bit complicated. And so therefore I won't be describing my solution, but I will be describing a much simpler solution, which I found out after reading the editorial. So yeah, I also won't be showing you the code because you guys can easily see the code of the editorial. That is much simpler and much easier to understand. Cool. So let's see what the problem is saying. So in this problem, for a zero indexed array A of size n, we call it good if for all the indices from 0 to n minus I, 0 to n minus 1, this value ai plus I is a perfect square, right? So we just have been provided with the number n in the input, and we have to construct a good array, which is an array where ai plus I is a perfect square for every I. That's the problem, a very small problem statement. So yeah, let's see how to solve this problem. So it turns out that the solution is not very difficult, but it's quite possible that a lot of people can overcomplicate this during the contest like I did, right? So yeah, okay, so let's see how we can solve this. So the way to solve this is that you start finding values from the right. So basically you start from n and then you go to 1 and then you start filling values somehow. So let's see how you can do that. So we will start at I is equals to n and end at I is equals to 1. So like I mean n minus 1 and 0, and build the permutation. Okay, so this is what we are going to do. Now let's see how we can do that. So let's say currently we are at I is equal to n. So for I is equals to n. So what we'll do is we'll iterate for the perfect square, which will be I n minus 1, right? So now the condition that we want to be satisfied is that p of n minus 1 plus n minus 1 is equal to a perfect square. So let's say it is y square. Okay, so we want something like this. So this means that p of n minus 1 is nothing but some number y squared minus n minus 1. Okay, that's true, right? So what we'll do is we will find the smallest y such that this condition is satisfied. Okay, and then what we'll do is we will keep using the same y for the previous few indices. Let's see how that's going to work out for us. So we'll find the smallest y such that p of n minus 1 is equals to y square minus n minus 1. That means we'll find the smallest y. So this should be changed. We'll find the smallest y such that y square minus n minus 1 is actually smaller than n minus 1, because we want p of n minus 1 to be smaller than n minus 1, right? So we'll just simply find the first y where y square minus n minus 1 is smaller than n minus 1. So basically Pn minus 1 now becomes y square minus n minus 1, right? And this is a number which is smaller than n minus, which is smaller than n, so this should be n, sorry. So yeah, this is a number which is smaller than n, and so this can be a part of our permutation, so we are simply assigning p of n minus 1 to be this number. Now if we use the same value of y for n minus 2, what we'll get is, we'll get p of n minus 2 is equal to y square minus n minus 2 is equal to y square minus n minus 1 plus 1. So this is nothing but p of n minus 1 plus 1, right? And if we keep doing this, what we'll get is, we'll get p of n minus 3 is equal to y square, it's basically p of n minus 2 plus 1, right? So our so basically the values will keep on increasing, so on and so forth, until we reach the value of n. So we will reach a value k where p of k will be equal to n, right? So if we keep doing this, naturally we'll come to an index k where p of k will be equal to n. Now what we can do is, now we are left to solve the exact same problem for k minus 1, right? Why? Because we have all the numbers from k plus 1 to n, right? Sorry, this is not true. So we started with this number y square minus n minus 1, and we have ended at n. So now we have the same problem for basically y square minus n minus 1 minus 1. Why? Because we started at this number. Let's say this number is x. So now we have the same problem for x minus 1. Because we just chose a suffix and we filled it with all the numbers starting from x till n. So now we have to fill all the numbers from 1 to x minus 1 to our permutation, and we have x minus 1 indices remaining. So now we are left with the exact same problem for n is equal to x minus 1. So now we can solve it recursively. Right? So yeah, this completes the solution to this problem. We just have to do some basic recursion here, and yeah, this problem is solved. So if you want to have a look at the code, then I would recommend just have a look at the editorials code. It's pretty simple to understand, and it uses the same solution which I have told you. So yeah, this completes the solution to problem C. Let's just quickly have a look at the last problem, problem D. So this was a really nice problem. Let's see what this is trying to say. Okay, so basically it's an interactive problem. Now if you don't have any experience with interactive problems, then I have actually made a video which explains how to solve interactive problems and what they are. So I will put the link to that video in the description so that you can check that out. Otherwise you're good to go. So let's talk about the problem. So basically there is a tournament in which there are 2 raised to the power n contestants, and the people who are adjacent will compete against each other in the first layer of matches, and then the winners will keep going forward, and then the same procedure will just keep repeating, that the people who are adjacent will compete with each other. That is, the person 1 will compete with person 2, 3 with 4, 5 with 6, so on and so forth, and the loser of the match gets eliminated and the winner gets moved to the next level of the game, right? And so if we just keep doing this, we will finally get a winner, and it will be a single player, right? So yeah, that's how the game is working. So our job is to tell who is the winner of the game, and to do so we can ask a few queries, and in the query basically we will just give 2 integers which are a and b. So these are the indices of any 2 players, and the judge will simply return us which among a and b has won more of the matches. So if a has won more matches than b, then we'll get 1. If b has won more matches than a, then we'll get 2. And if both of them have won the same number of matches, then we'll simply get 0 as our answer. So our job is to basically find who is the winner of the game, who is the winner of among all the players, and we have to do that in 1/3 of 2 raised to the power n plus 1 queries. So that's an interesting number right there. So yeah, this is the problem. N is only up to 17, so that 2 raised to the power n is not a very big number. So let's see how we can solve this. Okay, so one thing is that in a brute force solution, we can simply check the result of all the matches, right? So if we just simply check the result of all matches, obviously we will be able to figure out who is the winner. But the problem is, what is the number of matches? So number of matches. So since there are 2 raised to the power n players, the number of matches are going to be 2 raised to the power n minus 1. And the reason for this is that, let's say there are just 4 players. So if there are 4 players, then you can consider this as the semi-finals of, let's say, IPL. So there are 2 semi-finals and then there is 1 finals, right? So there are 3 matches. Similarly, if there will be 8 players, then you can consider this as the quarterfinals of a World Cup. So there, as you know, that there are like 4 quarterfinals, then there are 2 semi-finals, then there is 1 final. So there are 7 matches. So basically, for 2 raised to the power n players, there will be 2 raised to the power n minus 1 matches, which is nothing but 1 plus 2 plus 4 plus up till 2 raised to the power n minus 1. Okay. So if you simply ask the result of each, so now using a query you can know the result of each match, right? So now if you simply ask the result of each match, then you will get to know who is the winner of each match, and in using exactly 2 raised to the power n minus 1 queries, you will be able to figure out the answer. But the problem is that the query limit that we have, so the limit that we have is equal to 1/3 of 2 raised to the power n plus 1, which is around 2/3 of 2 raised to the power n. And we want 2 raised to the power n queries, which will definitely exceed the query limit. So the hint here is that instead of naively finding the result of each match, what we can do is that somehow, if we can figure out the winner of 3 matches using just 2 queries, then we are done, right? Why? Because if we are using 2 queries to figure out the winner of 3 matches, then we will use 2/3 of 2 raised to the power n, which is our limit, right? And since there is this ceiling function attached here, then we don't have to worry about that one query. So yeah, this is how we have to solve this problem. We have to somehow figure out the winner of 3 matches using just 2 queries. If we can always do that, if we can find an algorithm which always does that, then we are basically done. So now let's see how we will be doing that. So what we'll do is we'll focus on a group of 4 players. So we'll focus on a group of 4 players. Let's say these 4 players. So we'll be focusing on group of 4 adjacent players. So these 2 players will be playing a match. These 2 players will be playing a match, and the winner of these 2 will be playing a match, right? So this way we have 3 matches. So these are 3 matches. And what we'll do is we'll try to figure out the winner of all these. So we'll try to figure out who is the absolute winner among all these 4 people using exactly 2 queries, right? So yeah, obviously since these are 4 people, and so what happens is that the winner of this match and the winner of this match compete here, and the 2 people who are competing here will have one winner and one loser. And if we know the absolute winner of these 4 people, then we don't care what happened in the matches. We just want to know who is the absolute winner and who emerged victorious and went to the next level, right? So there will be one guy who will go to the next level, and he will be the winner of these 2, right? So we have to just figure that out using exactly 2 queries. So let's see how we can do that. So let's just arbitrarily assume that this guy is the winner, this is the loser of this match, and similarly this guy is the loser and this guy is the winner, right? So something like that. Uh, Now we have to do 2 queries to figure out the winner of among these 4 people. So what we'll do is in the first query we'll pick arbitrarily one person from the first group and one person from the second group. Okay, so let's see what results can we get. So let's say we pick the winner from the first group and the winner from the second group. So if that is the case, then if we ask the query, then we don't know what will be the result, because there is another match which will be played among these 2 winners, and whoever wins that match will have more wins. So the answer to this query will either be 1 or 2, right? Now we can pick the winner from the first group and the loser from the second group. Now in this case we definitely know what the answer will be, because this second person has not won any matches, but this first person has won at least one match, right? So the answer to this query will always be 1. Okay, cool. Now what happens is that we can have the exact opposite case, LW. So now this is the exact same case, so the answer will be 2 here always, right? And the fourth case is LL. So we pick a loser from the first game and we pick a loser from the second game, and in this case both of them will win exactly the same number of matches, so the answer will be 0. So these are the 4 cases that we have. Okay, cool. So let's say we name these 4 people. So the first group that we have was AB and the second group that we have is CD. Okay, and now let's say, now we'll do 2 queries, remember. So in the first query, so first query, let's say in the first query we match between B and D. So we send in B and D to the judge, and the judge will tell us whether B has won more matches or D has won more matches, or both of them have won the same number of matches. So let's say that the answer of this query is 1. So let's say the answer is Q1. Okay. So now we'll just make a few cases and we'll figure out who will be the absolute winner. So case 1 is when Q1 is equal to 1. Okay. So now if Q1 is equal to 1, we know for sure that B has won more matches than D. Okay. Instead of BD, let's just do BC. It doesn't really matter. So we know B has won more matches than C here, right? Another thing to notice here is that if you look closely among these 4 results, if we are getting a result of 1, then it is either the first situation or the second situation, right? And you can see clearly that in both of these situations we have one thing in common, and that is this W. So that means that the person that we have chosen from the first group is the winner of the first group. That means that B is greater than A, right? So B is always the winner. B is the winner. So B is the winner in the first group. Okay. So now what we'll do is we'll do another query. Remember that we are allowed to do 2 queries. So now we'll do another query, and in this query we will query between B and D. Okay. So this time we query between B and D, and now there are again 2 cases. So subcase 1 where we get a 1, and subcase 2 we get a 2. The reason that we can't get a 0 here is that we already know that this person B is the winner of the first group, right? So if this winner competes with the winner of the second group, then the answer will either be 1 or 2 for the next query, and if this winner competes with the loser of the first group, then the answer will always be 1. So we know that the answer of this Q2 can never be equal to 0. Okay. Now let's see what happens when the result of this query is equal to 1. So if this result is equal to 1, that means the number of wins of B is greater than the number of wins of D, and that now we have already established that B is greater than C and B is greater than A, and now we also know that B is greater than D, so B is the absolute winner among these 4. And now we have successfully determined the result of all these 3 matches using just 2 queries. And subcase 2 is when D has more wins than B. So in this case we know D has more wins than B, and we already know B has more wins than both C and A, right? It doesn't matter who has more wins among A and C, right? All that matters is that D has more wins than all of them, and so D is the absolute winner. Okay, so we can see that in this first case we have successfully determined who will be the absolute winner using exactly 2 queries. Now the second case is the exact same. The only difference is that here this time Q1 is equal to 2, which means that instead of, so here as you can see, Q1 is equal to 2 can only happen in one of these 3 cases, and in both of the one of these 2 cases, and in both of these cases in the second group we are always choosing the winner. So instead of the first group, this time we are choosing the winner from the second group. So this time we will simply do a query between, so this time we know that C is the winner on the second group, so we'll just query between A and C instead of B and D, and we'll repeat the exact same procedure. So this is not no different from, this is not like, this is like exactly the same as the first case. So we can say that in this case again we will be able to figure out who is the absolute winner using this Q2, right? And now the case 3 is much more simple. So it's when q1 is equal to 0. So now you know that q1 is equal to 0 is only happening in the second case. That means both of them are losers. So we know that both A and C are losers. So both B and C are losers. So simply find the result of AD, right? Because we know that A is the winner here and D is the winner here. So both A and D will be competing next. So we can simply ask for the winner of A and D, and that will be the absolute winner, right? So yeah, in this way we figure out the winner of of all these four people. That is, three games will be played among them, but we figure out the result of all these three games using exactly two queries. So the total number of queries that we use is somewhere around 2 raised to the power 2 by 3 into 2 raised to the power n, which is our limit. So this should ideally work. So yeah, this completes the solution. Let's just have a look at the code. Pretty simple to understand. So what I'm doing is I'm just keeping a vector, and I'm having these four values a, b, c, d, and I just make all these three cases which I just discussed. So this is q1 is equals to 1, this is q1 is equal to 2, and this is q1 is equal to 0. And we just keep figuring out the winner among these four people, and yeah, we keep reducing the size of our vector by 4 every time, because for every 4 people we replace them with their winner. So every time the size of our vector keeps getting reduced by 4, and finally we'll either be left with one person or two persons. So if we are left with two persons, we'll have to use another query to check who is the winner amongst them, and that will be our answer, right? So yeah, this basically completes the solution to problem D. So yeah, that's all for today. Thank you so much for watching, and I will see you in the next one.